How to solve circuits the right way, once and for all. Lecture 3. This is Vachev Orperian, and welcome to the Joys of Circuits Analysis. The material in these lectures is covered in my book, Fast Analytical Techniques in Electrical and Electronic Circuits. This is the second video on the extra element theorem, and in it I'm going to give you the general proof of the EET, and then I will specialize it to impedance elements in the determination of a transfer function, and after that I will specialize it to dependent sources in the determination of a transfer function. As you will see now, the proof of the EET requires very few steps. We begin with the block diagram of a linear time invariant circuit to which we will apply an excitation input 1 and pick up a response output 1. And as if a single excitation and a single response were not enough, we're going to apply another excitation and pick up another response output 2. We've seen this before, and we can write each one of these responses as a linear combination of each one of these excitations being applied to the circuit. Now we're going to convert the second excitation being applied to the circuit to a dependent excitation or to a dependent source. And we write an equation for that indicating that input 2 depends on the second response with a gain alpha. And we show that on the circuit diagram. Now this is a dependent source inside the LTI, and you're trying to figure out the transfer function output 1 over input 1. I want you now to think of this dependent source here as the troublemaker in your effort trying to determine the transfer function output 1 over input 1. And we call that the extra element. This dependent source, which we call the extra element, can be any one of your 4 controlled sources: a voltage-controlled voltage source, a voltage-controlled current source, a current-controlled current source, or a current-controlled voltage source. A voltage-controlled voltage source is just a voltage amplification typically used in modeling the output of an op-amp. A voltage-controlled current source is a transconductance used in modeling FETs and bipolar transistors. A current-controlled current source is just a current gain, and a current-controlled voltage source is a transistor resistance. All of these 4 sources have a gain alpha. Now you learned in your last video that a dependent source can also model an impedance or a conductance element, which means that if an impedance element is the troublemaker, it will be treated as an extra element. And now using elementary algebra, we can solve these 3 equations here to show that the transfer function output 1 over input 1 is given by this expression here. That's it. That's the proof of the extra element theorem. The extra element theorem basically tells you that the transfer function that you're looking for can be written in this form, where the extra element, which has a gain alpha, appears once linearly in the numerator and once linearly in the denominator, what they call the bilinear form. That's all it tells you, that you can cast your result in this form where the extra element gain alpha appears independently and separately on its own, once in the numerator and once in the denominator, all by itself. It is not present inside any one of these coefficients here. That's all it tells you. And now you're thinking, why did I have to watch 9 videos just to see 3 steps of linear algebra to prove the extra element theorem? And the answer should be quite clear now. And that is, you are never going to use this equation here to apply the extra element theorem. It just tells you the structure and the form of the extra element theorem that says that the extra element value appears by itself once in the numerator as a linear term and once in the denominator as a linear term. You are never going to have to write these three equations, solve them like this, and perform the algebra of A11, A22, A12, A21, and this whole business that you see in front of you. This is not the formula that you are going to use to apply the extra element theorem. What we're going to do is interpret these coefficients properly inside the circuit diagram and have an operational way of determining them. And that will become the extra element theorem or its application, proper application to circuit analysis. Now the whole point of the extra element theorem is that you want to determine this transfer function without doing the algebra involving the coefficients aij that you see in that equation. To do so, we rewrite that equation as follows. In it, we have introduced h0, script a bar, and Roman a bar. I'm going to show you how you determine these h0, a bar, and a script a bar operationally from the circuit diagram rather than from their algebraic expressions that you saw in the previous slide. Now I want you to look at these three equations here and draw a line from the middle going through the equal signs. On the right hand side you have your high school algebra dog work. On the left hand side you have the fast analytical techniques that I'm going to teach you. That's it. And that's how we're going to get into the extra element theorem. Hence, the problem of the determination of h, the full transfer function that you're after, is broken down to the determination of the following three independent and simpler calculations, which are defined as follows. h0 is the reference transfer function when alpha equals to 0. That means that you go into your circuit and you set the value of the extra element equal to 0. You take it out of the circuit, in other words, and you figure out the transfer function h0, which we call the reference transfer function. In addition, you calculate the inverse gain with respect to alpha and the null inverse gain with respect to alpha. You have seen plenty of these in the last many videos, except that I have never referred to them as the inverse gain with respect to the gain of an element. But you've seen it all. So I'm going to show you how you're going to determine h0 a bar and a script a bar operationally from the circuit diagram. And that will be the full import of the extra element theorem. Let us now show the determination of h0 operationally using the block diagram that we have for a general linear time invariant circuit. We said h0 is determined when the value of the extra element is set equal to 0, or the gain of the extra element is set equal to 0. That's alpha equals to 0. So we go into the block diagram of the general linear time invariant circuit and we set the value of alpha equals to 0. And that sets this excitation here equal to 0. That reduces the block diagram to this block diagram here, in which we determine the transfer function output 1 over input 1, defined as h0, the reference transfer function with alpha equals to 0. And here's a proof. If you call that a proof, if you look at this equation here, h is equal to h0 into 1 plus alpha script a bar over 1 plus alpha Roman a bar. Clearly, if I set alpha equals to 0, h coincides with h0, and therefore, operationally, when I go into my linear time invariant circuit and I kill the extra element by setting its gain to 0, I get the transfer function with alpha equals to 0. Not much of a proof. It's pretty straightforward, but that's what you do operationally. Let's move on to the next one, which is the Roman a bar, the inverse gain with respect to alpha, the extra element gain. It says To determine a bar, what you have to do is go into your linear time invariant circuit and replace the dependent source that you have here, the dependent excitation that you have here. You have to replace it with an independent version of it with a minus sign in front of it. A minus sign in front of it essentially means change the direction of the excitation. And set input 1 equal to 0. When you do this on your linear time invariant circuit, this is effectively what you get. You set the excitation equal to 0, you replace the dependent generator here with an independent version of it with a minus sign in front of it, which really means in the circuit you are reversing the direction of the generator at that point, the independent excitation at that point, and you determine the transfer function or the gain output 2 to minus ut. What you really are doing is you are figuring out how much does an independent excitation at the point where the dependent excitation is talk back to the value on which the dependent generator depends on. This is the talk back from the point where the dependent generator is using an independent generator to see how much it talks back to the variable on which it depends. It's an inverse. That's why we call it an inverse. It's an inverse gain. That's why we call that as such. To prove that this is correct, we know that a bar, Roman a bar, was defined as minus a22. You have to go back to that slide of the proof of the extra element theorem, and you see in it we defined a bar as minus a22. Now, who said this operation really yields a bar? Well, the proof is as follows. You set input 1 to 0. That's what we said you have to do. You set the excitation of the transfer function to 0. The transfer function that you are after, output 1 over input 1. That's the transfer function you're after. You know what its excitation is. It says set it equal to 0. So we set it equal to 0 there. And look at output 2 with input 1 equal to 0. That takes this term away. So now output 2 over input 2 with input 2 being an independent version of the original dependent generator. You put that in there and you find out that a bar indeed now comes out to be minus a22. So this is the operational way of determining minus a22. You go back in your circuit, you remove the dependent generator and you replace it with an independent version of it pointing in the opposite direction. You set the excitation equal to 0 and you figure out this reverse gain. That's it, and that yields to you minus a22. This is the operational technique of determining Roman a bar, the inverse gain with the excitation set equal to 0. Good. Let's go to the next one. Now we want to see the determination of a script a bar, the null inverse gain. Well, the first part of the operation is the same. Replace the dependent generator with an independent version of it with a minus sign in front of it, which means let it point in the opposite direction. But this time, instead of making the excitation equal to 0, minus ut and ui1 together are going to null the response. They're going to make uo1 equal to 0. When you do that operation, this is what you get for a block diagram. Input 1 is present. The dependent generator has been replaced with an independent version of it pointing in the opposite direction. And the two together are nulling the response. In the first case, when you were doing Roman a bar, the null inverse gain, you were setting this equal to 0. When you do the script a bar, then you're setting the response to 0. And under these conditions, you determine the gain output 2 to minus ut, and that gives you a bar. Who said this is true? Well, let's prove it. let's go into these two equations that we wrote earlier on, and let us adjust the input 2 with the independent generator minus ut. Let us adjust input 1 with respect to minus ut so that the output 1 has been nulled. When you do that and you solve the ratio of output 2 to ut from these three equations, you see that it turns out to be equal to this massive relationship between the coefficients a12, a21, a11, a22 divided by a11. That turns out to be, we defined this as a script a bar, the null inverse gain. So to determine null inverse gain, you don't have to go through the operation of multiplying a12 with a21, subtracted for a11, a22 divided by a11, and what have you. You don't need to do this algebra. That's your high school algebra. That's your dog work. You do it on the circuit by replacing the dependent generator with an independent version of it. That generator, along with the excitation of the transfer function, will null the response, and when that happens, you just determine the gain output 2 to minus ut, and that will give you the script a bar. And you're done. Let us see now if there's another way of taking the extra element out of the circuit. The way that I just showed you was to set the value of the extra element equal to 0. But there's another way that you can do it actually. You notice in this equation here that we derived for the extra element theorem that I can divide up and down by alpha, which when I do, I get this form here. Alpha here will cancel, and I can write this in this form here. H equals to h infinity into 1 plus 1 over alpha script a bar over 1 plus 1 over alpha Roman a bar. And I see that when alpha goes to infinity, h infinity, which is given by h0 Roman a bar over script a bar, which you don't have to worry about, that corresponds to the transfer function with the value of that extra element taken to infinity. So there are really two ways you can make the extra element drop out of the picture. Either take its value alpha equal to 0 or alpha equal to infinity. Both will work. And which way you're going to do it? You're going to do it with the way which is most convenient for you. In fact, the one that is most reasonable for you to do. For instance, if alpha was the gain of an op-amp, it is reasonable to assume that alpha typically is of infinite value. It's not infinite, it's 10 to the 6, 10 to the 7, 10 to the 5. That's pretty darn large. So it is reasonable to say that, well, let me assume it's infinite and see what my transfer function is. And for all those op-amp circuits, cookbook op-amp circuits, you have computed all those gains with ideal op-amps with a gain of infinity. And it turns out the gain is not actually exactly what you obtain from the perfect ideal conditions of infinite gain. It's slightly different than that. How slightly it is different from that? It is slightly different from that by this factor here. But let's leave that later on when we do actual examples. So this is the second form of the extra element theorem, in which the extra element is taken out of the circuit or made to drop out of the circuit from the calculus of the circuit by allowing its value first to go to infinity, calculating the transfer function with the value of alpha infinity, then reinstating it into the picture of the final answer in this form here, where you have to have script a bar computed and Roman a bar computed. Now the calculation of script a bar and Roman a bar is identically the same as before, meaning when you were taking alpha equal to 0. That's not affected by it at all. Those values of script a bar and a Roman a bar are computed identically the same way as we talked about before. The operational way of determining has nothing to do with the way you take the extra element out of the picture, whether you let its value equal to 0 or whether you let its value equal to infinity. It's just that when you let the value equal to 0, you use the previous form that I showed you on the previous slide for the extra element theorem, and if you take its value to go to infinity, you use this form. It gives you two choices, which is very good. So in this case now we call h infinity the reference transfer function when alpha equals to infinity. Before h0 was the reference transfer function when alpha was equal to 0. The remaining are identically the same as before. Let me show you now the determination of h infinity on the block diagram. Here's our block diagram here for the general linear time invariant circuit. This is our dependent source input 1, a dependent source that depends on output 2, UO2. Before I took value of alpha equals to 0, and I showed you what that would look like on the block diagram. Let me show you what this looks like when you allow alpha to go to infinity. When I allow alpha to go to infinity, then output 2 goes to 0. What does that mean? Have you seen this before? Of course. In an ideal op-amp circuit with an infinite gain, the fact that the differential input voltage between the inverting and non-inverting terminal 0 is this here. Output 2 is 0. Output 2 is not such a thing as output, it's a response, which we called output 2. The differential input voltage at the input of the operational amplifier is a response inside that circuit. And when the gain of the operational amplifier goes to infinity, that response, that voltage between the inverting and non-inverting terminal, shrinks down to 0. And this is exactly what this is saying here. When you let alpha go to infinity of a dependent source here, then alpha 2 goes to 0. And this is what that picture is. And this is where you compute your output over input. This is the computation of the gain of an ideal op-amp circuit. The one that comes to your mind is an inverting op-amp with R2 and R1, resistors R2 in the feedback, R1 in the input, and the gain is minus R2 over R1. The gain of the op-amp, the fact that it is infinite, doesn't get into the picture. It has dropped out of the calculus of determining the transfer function of that circuit. And now, in the next 14 slides, I'm going to saturate you with the application of AET to an impedance element, once taken out as 0 and once taken out as infinity, and to the 4 dependent sources, each once taken out as 0 and once taken out as infinity. And I believe by the end of these slides, the extra element theorem will have sunk in quite properly. Why don't we start with the application of the ET to an impedance element Z? We said earlier that an impedance element Z can be modeled as a dependent voltage source that depends on the current through its own terminals according to Ohm's law. V equals to alpha I. Alpha is the gain of that dependent voltage source equal to the value of the impedance element Z1. When we do that, then according to the extra element theorem, that any transfer function of an LTI circuit containing Z1 can be written in the following form. H equals to H0 into 1 plus Z1 into script A bar over 1 plus Z1 Roman A bar, where script A bar is the inverse gain with respect to Z1 with the response null, and Roman A bar is the inverse gain with respect to Z1 with the excitation set equal to 0. H0 is the value of the transfer function when the value of Z1 is 0. That is to say, you go into your circuit and you short circuit that element and you figure out the transfer function H0. Then you reinstate that element Z1 into the final answer by doing additional 2 calculations. The null inverse gain with respect to Z1 and the inverse gain with respect to Z1 with the excitation set equal to 0. And we're going to show each one of these H0, Roman A bar and script A bar on the block diagram in the next few slides. Let's begin with the replacing Z1 with the voltage source that depends on the current through it with a gain Z1. So we have our original circuit in which there's an element Z1 that is the troublemaker. We designate this as the extra element. Once we do that, we replace Z1 with a dependent voltage source V that talks to the current through it I. Now, this circuit here and this circuit here are identical because this dependent voltage source here represents Z1, and therefore everything else in this circuit that you compute using this circuit here is identically the same as what you would compute for this circuit here. In relation to the general form of the extra element theorem that we talked earlier, input 2 that we had there is V, and output 2 is I, and we made input 2 be dependent on output 2 with a gain alpha, and alpha now is just C1. And that's how we made this dependent source here represent this impedance element C1. Let us now determine the three components of the extra element theorem. The first one is H0. And we're going to do that, we said, operationally on the circuit diagram by setting the gain of the dependent source equal to 0. The gain of the dependent source here is Z1. And when you set that equal to 0, that really amounts to nothing more than short-circuiting that resistor. Let us see. Let us set that equal to 0. You have a dependent source here, a voltage source here, whose value is 0. That's a short circuit. So that goes out of the picture and a short circuit comes in its place. And now you're going to compute this transfer function, output 1 over input 1, with that element Z1 shorted. And that yields H0. And this is your first computation, which is shown in yellow colors. Let's move on next to the determination of A bar, the inverse gain with respect to Z1 with the excitation set equal to 0. When we do that on this block diagram, UI1 drops out because we set it equal to 0, and we are left with this configuration here. The next thing that we have to do after we set the excitation equal to 0 is that we replace the dependent generator V equals to IZ1 with an independent version of it pointing in the opposite direction with a minus sign in front of it, which means that instead of putting a minus sign there, you can just reverse the direction of this generator here. And now you have VT pointing in this direction, and you want to compute how much VT talks back to I. So you want to compute the inverse gain I over VT with this excitation set equal to 0. And that is nothing more than the input conductance looking into port 1, the ordinary driving point conductance looking into port 1, which means set all independent excitations equal to 0. And this is the operational way of determining Roman A bar, the inverse gain with respect to Z1 with the excitation of the transfer function set equal to 0. The driving point admittance looking into port 1 with the excitation set equal to 0, I over VT. Let's move on to the null inverse gain with respect to Z1, but this time with the response nulled. How do we do it? Well, the whole operation is the same as before. You go in, you replace the dependent generator here with an independent version of it pointing in the opposite direction. And this time you're going to calculate the gain I over Vt, which is the inverse gain, but this time Vt and UI1 are going to null the response. And it is under these conditions that you're going to compute the input admittance, I over Vt with output 1 null. You see that in one case it is the input that is being set equal to 0. In the second case, which is a numerator computation, it is the response that's being nulled. In the denominator, it is the excitation that's been set equal to 0. A concept that we're quite familiar with. So now script A bar, I over Vt, the null driving point admittance looking into port 1 is computed operationally following this block diagram here. And now let us summarize what we just did by taking the value of the extra element z equal to 0 and applying the extra element theorem. What we did first was, when we set the value of the extra element equal to 0, we went at that port where the extra element was connected and we replaced it with a short circuit and we determine H0, our yellow computation, the transfer function with that element taken out. So in this block here, that element is out of the picture. Next, we had to perform two additional calculations, which were the inverse gain with respect to Z1, once with the response nulled and once with the excitation set equal to 0. The response null calculation was for the numerator, and with the excitation set equal to 0 was for the denominator. So in the next block, what we did was calculate the input admittance looking into port 1, the ordinary driving point impedance looking into port 1, with the excitation, of course, set equal to 0. And last, what we did was we computed the null input admittance looking into port 1, but this time with the response nulled. And we accomplished that with the applied voltage source, or you could have easily used the current source if you wanted to, it didn't matter, with a voltage source connected there and the original excitation in the circuit of the transfer function. Together they null the response, and under those conditions you determine the input admittance. And with script y1 and Roman y1 being computed, you replace that inside the extra element theorem with H0 computed from this calculation here with the element shorted. Each one of these three calculations is simpler than the original circuit because they don't contain the troublemaking element Z1. That's why the application of the extra element theorem, by breaking it down into three components, three separate calculations, makes the algebra of the computation of the transfer function much easier. So what we have really is one difficult step from the beginning, which will break it down into three easy calculations. One difficult equals three easy. And that's the application of the extra element to an impedance element when you first choose its value to be equal to 0. Let us now consider taking the extra element Z1 out of the picture by taking its value to be infinite. When we choose to do that, this is the form of the extra element theorem that we use, in which H0, H prime 0 that is to say, is the value of the transfer function with Z1 infinity. We called this H infinity earlier on. We can call it H prime 0 here. You have the full freedom to call these things anything you like, whatever suits you. So I'm calling it now H prime 0. When we do that, we take the element Z1 out of the picture by taking its value infinity, and we get this block here in which we compute the transfer function output 1 over input 1 with Z1 taken as infinity. The remaining two computations, where you determine the admittance looking into port 1 with the excitation set equal to 0 and the admittance looking into port 1 with the response null, is identically the same as before. That doesn't change. That doesn't depend on how you decided to take the extra element out of the picture, whether you decided to take it as a short or you decided to take it as an open. That doesn't change at all. So these two computations are the same as before. It's just that the constant that appears up front, or the factor that appears up front, is different. One corresponds to the reference transfer function with the value of the extra element taken as infinity, and the other one, or the previous one, is when you consider the value of the transfer function with the extra element value set equal to 0. So once again, this being the difficult calculation, it has been broken down into 3 separate, simpler calculations because none of these contain the troublemaking element z1, and we have one difficult step replaced by 3 easy steps. You notice here that, of course, you can either write it this way or you can write it this way, where instead of writing z1, you write it as a conductance, and it appears exactly in the same form as that of the extra element. The extra element now is considered to be a conductance rather than impedance. It's the same animal. It's just that what you decide to call it, Z1 or Y1. That's it. And now we specialize the extra element theorem to a voltage-controlled voltage source as shown in this block diagram here. We're trying to compute the transfer function in a linear time invariant circuit that contains a dependent voltage source mu0 V epsilon, where V epsilon is the voltage across some impedance element inside this circuit. In computing this transfer function, this is the element that is causing us trouble. It's giving us difficulty, so we would like to take it out. We have two choices. Either we set mu0 equal to 0 at first, or we set mu0 equal to infinity. We will try the second choice first. We let mu0 go to infinity, and the extra element takes the following form. Rather, the extra element theorem takes the following form. In it, we have h infinity, which is the transfer function mu0 over mu1 with the value of mu0 taken infinity. This is followed by a correction factor in which we'll compute the null inverse gain with respect to mu0, in which we null the response mu01, and the inverse gain with respect to mu0 with the excitation set equal to 0. Let us show the computation of h infinity on the block diagram here. We let mu0 go to infinity, and when we do that, the voltage on which this dependent voltage source depends, V epsilon, shrinks to 0. This should remind you of ideal op-amp circuits in which the differential input voltage between the inverting and non-inverting terminal of an ideal op-amp with infinite gain is 0. Hence, we compute h infinity, and this is our yellow calculation. It is much simpler, of course, than this computation here, the entire computation, or the computation of the transfer function in this circuit, because the circuit has been simplified by rendering the op-amp ideal with infinite gain. You're all familiar with that. So the second computation we have to do is the inverse gain with respect to mu0 with the excitation set equal to 0. In this diagram here, we compute the inverse gain, V epsilon over Vt. We call it inverse gain because really what we're trying to figure out is how much does an independent voltage source connected at this point here talk back to the epsilon, V epsilon, which is the voltage on which this dependent voltage source depends. And now this is our green computation. And finally, we compute the null inverse gain. Here, just like in this case, we replace the dependent voltage source with an independent voltage source pointing in the opposite direction. And Vt, together with the input of this transfer function, we null the response. And under these conditions, we compute the inverse gain, V epsilon over Vt. This is called the null inverse gain. That's our red computation. And having computed the null inverse gain, the ordinary inverse gain, and H infinity, we substitute these in the expression of the extra element theorem, and we obtain our full transfer function. What you have here is that the computation of H directly from this whole circuit is complicated because of the presence of this dependent voltage source here. We remove it out of the circuit and we break the circuit down into 3 separate calculations which do not involve this dependent source here. By doing that, we calculate H infinity, the null inverse gain, and the ordinary inverse gain. So first you compute the transfer function with this element taken out as infinity, and then you reinstate mu 0 with the help of these 2 additional computations and the use of this extra element theorem formula. And now we try our second choice for mu 0. We let mu 0 go to 0. And in this case, the form of the extra element theorem is as shown here. First, you compute H0, which is the transfer function with mu 0 set equal to 0, followed by this correction factor in which we have computed the null inverse gain and the ordinary inverse gain. These 2 computations are the same as the previous one, because these 2 computations do not depend on how you choose to take the extra element out of the circuit, whether you take it out as 0 or you take it out as infinity. The only thing that changes is this factor that appears up front, and that's H0. And we show that in the following block diagram. When we let mu 0 equal in this dependent source here equal to 0, mu 0 you make it equal to 0, that dependent source becomes a short circuit. Certainly this one here is much simpler than this circuit here, for which you can compute H0, and that's your yellow computation. The other 2 computations are identically the same as before, and I don't have to go over it. The ordinary inverse gain with the excitation set equal to 0, and the null inverse gain with the response nulled, in which you compute script mu bar. And you substitute these 3 computations into the expression of the extra element theorem, and you get your full transfer function. So you have 2 different analytical expressions for the transfer function. In the first case, the expression involved mu 0 as taken out as infinity, and in this one, mu 0 taken out as 0. You may ask, well, which one do I use? That's entirely up to you. If typically mu 0 is of large value, it is reasonable to use the previous choice. It doesn't make any difference though. If you want to use mu 0 equal to 0, this is equally a correct expression, but perhaps not as relevant to the circuit because the factor that appears up front is not of much interest. Imagine in an ideal op-amp circuit, you do your calculation first assuming the gain of the op-amp is 0, and then you bring it in as mu 0 with some large value. Then this is not a very nice form, even though analytically it's fine. It was calculated using 3 easy steps, but it is not as relevant. So your choice of how you're going to take an element out of the circuit sometimes is motivated by what is most relevant to the application of that circuit. And now we specialize the extra element theorem to a current-controlled voltage source as shown in this block diagram here. We want to compute the transfer function of the circuit that contains this dependent source. It's a transresistance source. It's a voltage source that depends on the current in some branch inside the circuit, I epsilon. And we have 2 choices again to take this element out. This is the extra element. It's the one that's causing us trouble in the determination of this transfer function, and we'd like to take it out. We have two choices. Either you set rho 0 equal to 0 or rho 0 to infinity. Let us try first setting rho 0 equal to 0. And in this case, the transfer function, according to extra element theorem, has this form. H0 is the transfer function that you obtain by setting the value of rho 0 equal to 0. And then you compute the null inverse gain with respect to rho 0, script r bar, and the inverse gain with respect to rho 0 with the excitation set equal to 0. Let us show this on the block diagram. H0 is determined by setting rho 0 equal to 0, our choice for the extra element being taken out of the circuit. And that means when you put rho 0 here equal to 0, that voltage source becomes 0. That's a short circuit. So the first transfer function you compute, H0, is obtained by short-circuiting this dependent voltage source. And for that you compute H0. This is our yellow calculation. Next, you're going to compute the inverse gain with respect to rho 0 with the excitation set equal to 0. To do so, you replace this dependent voltage source here with an independent voltage source pointing in the opposite direction, and you set the excitation equal to 0. And then you determine the inverse gain, I epsilon over Vt. And that's the inverse gain with respect to rho 0, Roman bar, I epsilon over Vt. And that's our green calculation. And then finally, you compute the null inverse gain, where again you replace the dependent source with an independent source, voltage source as shown, pointing in the opposite direction, and you null the response and you determine the inverse gain, I epsilon over Vt under null response conditions. And that gives you your script R bar. When you substitute H0 R bar and script R bar in the expression of the extra element theorem, you get your full transfer function. Each of these calculations, once again, is simpler than the calculation over the entire circuit without having to take this element out. And the reason for that is this trouble-causing element does not exist inside any one of these three circuits. Our second choice for taking this extra element out is to let the value of rho 0 go to infinity. And in that case, the form of the extra element theorem is as shown here. In this case, we compute h infinity, which is the value of the transfer function, when we let rho 0 go to infinity. And we show that on this diagram here. We let rho 0 go to infinity. The current on which this dependent source depends, when you let rho 0 go to infinity, the value of that current shrinks to 0. And it is under these conditions that you compute the transfer function output 1 over input 1 with rho 0 gone infinity and this current has shrunk to 0. And that's your yellow calculation. This is again a simpler calculation than what you would have in this circuit because it is very similar to ideal op-amp circuit calculations. The second calculation that you perform is the inverse gain with respect to rho 0 with the excitation set equal to 0. To do this computation, again, you replace the dependent source with an independent version of it, pointing in the opposite direction. The dependent source here is a voltage source, so you replace it with an independent voltage source pointing in the opposite direction. And with the excitation set equal to 0, you determine the inverse gain, I epsilon over Vt. This is the same computation that we did in the previous slide. Identically the same. It has nothing to do with our choice whether we took rho 0 to be equal to infinity or 0. This is exactly the same computation as before. Likewise, the null inverse gain is exactly the same as before. Script r bar. And when you substitute h infinity r bar and a script r bar in the expression of the extra element theorem, you get your full transfer function. Now I'm going to repeat the application of the extra element theorem to a current controlled current source as shown in this diagram here. So we want to compute the transfer function output 1 over input 1, and we have a dependent current source in our circuit that's giving us trouble, and we'd like to take it out. We have two choices. Either you set mu 0 equal to 0, or you set mu 0 equal to infinity. Let us go our first choice, mu 0 equal to 0, and this is the form of the extra element theorem, where h0 is the transfer function which we compute setting first the value of mu 0 equal to 0. And we show that on this block diagram here. When I set mu 0 equal to 0, then this current source has a value of 0, which means that it is an open circuit. So what you're going to do really is compute the transfer function output over input with this dependent current source open circuited, taken out of the circuit. And this gives us h0, and that's our yellow computation. Next, we compute the inverse gain with respect to mu 0 with the excitation set equal to 0. To do so, we replace the dependent source here with an independent version of it pointing in the opposite direction. Our dependent source in this case is a current source. So we replace it with an independent current source pointing in the opposite direction. And with the excitation set equal to 0, we find the inverse gain, I epsilon over IT, and we call that U bar. And this is the inverse gain with the excitation set equal to 0 with respect to mu 0. And finally, we compute the null inverse gain with respect to mu 0, same way by connecting an independent test current source pointing in the opposite direction in the place of the dependent current source, and we null the response. And we compute I epsilon over IT under these null response conditions. With U bar and U script bar and H0 computed, we substitute these in the extra element theorem and we get our full transfer function. Each of these calculations is simpler than the full calculation of this circuit, which involves the presence of the dependent source there. Our second choice of taking this dependent source out was to let its gain value, to go to infinity. When we do that, the form of the extra element theorem is as shown here. So first we're going to compute h infinity as shown in this block diagram here. We let mu 0 go to infinity. And in this case, when you let mu 0 go to infinity, the current on which this dependent current source depends shrinks to 0. And we compute the transfer function output over input h infinity under these conditions of this current having shrunk to 0 while this has gone to infinity. And this is our yellow calculation. Again, this is a simpler calculation than the calculation in this circuit because this is very similar to ideal op-amp circuit calculations. Next, the calculation of the inverse gain with the excitation set equal to 0 is exactly the same as before. We said this calculation here does not depend on your choice of the extra element being taken out as 0 or as infinity. And the null inverse gain, same as before, same value, same expression that we obtain. It is only h infinity or h0 that changes up front. And once again, we have the transfer function in this form now. finally, I'm going to show you the extra element theorem applied to a voltage-controlled current source, as shown in this diagram here. So you're trying to figure out the transfer function output 1 over input 1 in the presence of this transconductance. And this is giving you trouble. That's the troublemaker. So what are you going to do? You're going to take it out of the circuit with one of two choices. Either you let G0 go to 0, or you let G0 go to infinity. Why don't we try G0 equal to 0? In which case, the form of the extra element theorem is as shown here. So, we're going to compute first the transfer function with G0 equal to 0. When we do that, G0 equal to 0, this current source has a value of 0. So, drops out of the picture. It's open circuited. And we figure out our transfer function output 1 over input 1 with this current open circuited. And that's our yellow calculation. Next, we compute the inverse gain with respect to G0 with the excitation set equal to 0. So we set whatever this excitation here is to 0. We replace the dependent source with an independent version of it pointing in the opposite direction. In this case, this is a dependent current source, so we replace it with an independent current source pointing in the opposite direction. And we compute the inverse gain V epsilon over IT. This is the inverse gain with respect to G0. You notice that this has the resistance of ohms, whereas the G0 has the units of inverse ohms. It's an inverse gain. And this is our green calculation. And lastly, we compute the null inverse gain. Same deal, we replace the dependent source with an independent current source pointing in the opposite direction, and we let IT and input 1, the excitation of our transfer function, null the response of the transfer function, and under these conditions we determine the inverse gain V epsilon over IT. And that's our red calculation. Having calculated each of these, we substitute them in the expression of the transfer function and we get our full transfer function. Now, if we wanted to choose G0 as infinity, then the form of the transfer function would take this form here. And the computation of H infinity is shown in this block diagram here. You let G0 go to infinity. Whatever this dependent source depends on, when you let its amplitude, magnitude go to infinity, then whatever it depends on shrinks to 0. And you compute the transfer function with G0 going to infinity. This is a simpler calculation than this one because it's very similar to ideal op-amp circuit calculations. Next, you compute the inverse gain with respect to G0 with the excitation set equal to 0. But this is exactly the same thing as we did in the previous slide for the case of G0 going to 0. And I repeat, the inverse calculations, whether it's null or ordinary, are not affected by your choice of your extra element, whether you take it out as 0 or you take it out as infinity. So this is the same as before, and likewise the null inverse gain computation is exactly the same as before. Same result, that expression doesn't change. The expressions that you obtain for G bar and script G bar are the same in this case and in the previous case. And with these computed, you can compute the full transfer function using this form of the extra element theorem. And now you have seen the application of the extra element theorem in all possible cases for impedance elements taken out 0 or infinity, or any one of the 4 dependent sources taken out as 0 or as infinity. And that's the extra element theorem. In my next set of videos, I'll be applying this theorem to different circuits. And we'll see you then. Thank you.